close your eyes for a moment. Imagine floating in absolute darkness. Not the darkness of a room with the lights off, not the darkness of a moonless night on a country road, but a darkness so total, so profound, so infinite that there is literally nothing to see in any direction. No stars, no galaxies, no planets, no light of any kind. Just an endless, silent, cold void stretching in every direction forever. Now open your eyes and realize something terrifying. That darkness is not imaginary. That darkness is real, and it exists right now at this very moment, surrounding the thin shell of light we call the observable universe. Beyond the farthest galaxy, beyond the oldest photon, beyond the reach of any telescope ever built or ever imagined, there is a realm of absolute cosmic mystery that no human being has ever seen, and perhaps no human being will ever see. But here is what makes this story extraordinary. A machine is trying. Right now, as you listen to these words, a golden mirror the size of a tennis court is floating silently in the void of space, 1 million miles from Earth, staring into the deepest darkness the universe has to offer. And what it has found there has shaken the foundations of everything we thought we knew about reality. That machine is the James Webb Space Telescope. And what it has discovered beyond the edge of the universe is not just surprising. It is not just unexpected. It is, in the most literal sense of the word, impossible. At least, it should have been impossible according to everything we believed about the cosmos. Galaxies that formed too early. Black holes that grew too fast. Stars that may be powered not by nuclear fusion, but by the annihilation of dark matter itself. A cosmic fog that was cleared by forces we do not yet understand. A fundamental disagreement in the laws of physics that suggests either our measurements are wrong or our understanding of reality itself is broken. And perhaps most haunting of all, hints, whispers, chemical fingerprints in the atmospheres of distant worlds that might, just might, be the first faint signatures of life beyond Earth. This is not science fiction. This is what the James Webb Space Telescope has actually discovered. Every single thing I just mentioned is real, documented, published in peer-reviewed scientific journals, and confirmed by teams of astronomers working around the clock to understand data that refuses to fit neatly into the models we have spent decades building. And today, we are going to go through every single one of these discoveries. Not quickly, not superficially, not with hand-waving explanations and oversimplified metaphors. We are going to go deep. We are going to explore every angle, every implication, every twist, every mystery, and every terrifying possibility. We are going to start at the very beginning, with how this extraordinary machine works and why it was built. Then, we are going to travel across 13.8 billion years of cosmic history, from the moment the universe became transparent to the present day, exploring everything JWST has revealed along the way. And when we reach the end, we are going to confront the deepest question of all. What is beyond the edge? What lies out there, past the last photon, past the cosmic horizon, in the darkness that no instrument can penetrate? Is it more of the same? Is it something fundamentally different? Is it another universe? Is it infinite? Is it nothing at all? Before we begin that journey, I want you to do something. I want you to take a moment and think about the most mind-blowing fact you know about the universe. Maybe it is the size. Maybe it is the age. Maybe it is the number of stars. Whatever it is, hold that thought. Because by the end of this video, I promise you that what you considered mind-blowing will feel like a warm-up. The real revelations are ahead. And if you are the kind of person who lies awake at night wondering what is out there, wondering why we exist, wondering whether we are alone, then you are in exactly the right place. So subscribe if you have not already, Hit that notification bell so you never miss a video like this. Drop a comment right now telling me what you think is beyond the edge of the universe, because I genuinely want to know your theory, and I read every single comment. And now, let us begin. To understand what the James Webb Space Telescope has discovered, you first need to understand why we built it in the first place. And to understand that, you need to understand a fundamental truth about the universe that most people never think about. When you look at the sun, you are not seeing the sun as it is right now. You are seeing the sun as it was 8 minutes and 20 seconds ago, because that is how long it takes light to travel the 93 million miles from the sun to your eyes. When you look at the nearest star beyond the sun, Proxima Centauri, you are seeing it as it was 4.24 years ago. When you look at the Andromeda Galaxy, our nearest large galactic neighbor, you are seeing it as it was 2.5 million years ago. 2.5 million years. That means when you look at Andromeda through a telescope, you are seeing light that left that galaxy when our ancestors were just beginning to walk upright on the plains of Africa. Homo habilis had not yet appeared. The Stone Age had not yet begun. And that light, that ancient light, was already on its way to us, traveling at 186,000 miles per second, crossing the incomprehensible gulf between galaxies, destined to arrive at this exact moment in history so that you could see a galaxy as it existed in the deep past. This is not a metaphor. This is not a poetic way of speaking. This is literally how the universe works. Light travels at a finite speed, and because of that, every time you look at something far away, you are looking backward in time. The farther you look, the further back in time you see, and this leads to an astonishing realization. If you had a telescope powerful enough, you could look so far away that you would see the universe as it was billions of years ago. You could see the first galaxies forming. You could see the first stars igniting. You could see the universe in its infancy, just a few 100 million years after the Big Bang, when everything was young and hot and chaotic and new. This is exactly what the James Webb Space Telescope was designed to do. It is, in the most literal sense, a time machine. Not in the science fiction sense of traveling backward through time, but in the very real, very physical sense of collecting ancient photons that have been traveling across the universe for over 13 billion years. Photons that carry within them the story of what the cosmos looked like when it was practically newborn. But building such a telescope was not simple. In fact, it was one of the most challenging engineering projects in human history. And to understand why, you need to know about a phenomenon called redshift. Here's the problem. The universe is expanding. Not in the way that a balloon expands, with galaxies flying outward into empty space. Rather, space itself is expanding. The fabric of the cosmos is stretching in every direction, and as it stretches, everything in it moves apart from everything else. Now, when space stretches, the light traveling through it also stretches. Imagine drawing a wave on a rubber band and then pulling the rubber band. The wavelength of the wave gets longer. The same thing happens to light as it travels through expanding space. Its wavelength gets longer. And here is the crucial point. Visible light, the kind our eyes can see, has relatively short wavelengths. When that light stretches, it shifts toward longer wavelengths, past the red end of the visible spectrum, into a realm of light that our eyes cannot see at all. This is called infrared light. We cannot see it, but we can feel it. It is what we experience as heat. So here's the problem for astronomers. The earliest galaxies, the ones that formed in the first few 100 million years after the Big Bang, emitted light in the ultraviolet and visible spectrum. But that light has been traveling for over 13 billion years through an expanding universe. By the time it reaches us, it has been stretched so much that it is no longer visible light. It is infrared, completely invisible to our eyes and to any telescope designed to see visible light. This is why the Hubble Space Telescope, as extraordinary as it was, could only see so far back in time. Hubble was designed primarily to see visible and ultraviolet light. It had some infrared capability, but it was limited. To see the very first lights in the universe, we needed a telescope designed from the ground up to see infrared light. We needed a telescope that could collect the faintest, most red-shifted, most ancient infrared photons in the cosmos. We needed the James Webb Space Telescope. The James Webb Space Telescope, or JWST, or simply Webb, is unlike any telescope ever built. Let me walk you through what makes it so special, because the engineering alone is enough to make your jaw drop. First, the mirror. Every telescope needs a mirror to collect light. And the bigger the mirror, the more light it can collect, and the fainter the objects it can see. Hubble's mirror was 2.4 meters in diameter, about 8 feet. Webb's mirror is 6.5 meters in diameter, about 21 feet. That is nearly 3 times wider, but because light collection scales with the area of the mirror, Webb actually collects roughly 6 to 7 times more light than Hubble. But here's the twist. You cannot launch a 6.5-meter mirror into space in one piece. No rocket fairing is large enough to fit it. So the engineers at NASA, the European Space Agency, and the Canadian Space Agency came up with an ingenious solution. They built the mirror out of 18 separate hexagonal segments, each about 1.32 meters across, made of beryllium and coated with a microscopically thin layer of gold. Why beryllium? Because it is lightweight and holds its shape incredibly well at extremely cold temperatures. Why gold? Because gold is one of the best reflectors of infrared light. Each of these 18 segments is equipped with 7 tiny actuators, motors that can adjust the segment's position with nanometer precision. That is the precision of a few atoms. When Webb was launched, these 18 segments were folded up like origami inside the rocket. After launch, they slowly unfolded in space, and over the course of several months, the actuators aligned all 18 segments to act as a single, perfect mirror, focusing infrared light with exquisite precision. But the mirror was only half the challenge. Here is the other half, and it is the part that nearly killed the entire project. Infrared light is heat radiation. Everything that has a temperature above absolute zero emits infrared light. Your body emits infrared light. A warm cup of coffee emits infrared light. The sun absolutely floods space with infrared light. And here's the problem. If the telescope itself is warm, it will glow in infrared, completely overwhelming the faint ancient light it is trying to detect. It would be like trying to see a firefly while standing inside a spotlight. The solution was to make the telescope incredibly, almost impossibly cold. Webb needs to operate at temperatures around minus 233 degrees Celsius, which is about 40 Kelvin, just 40 degrees above absolute zero. To achieve this, the engineers built a sun shield. And when I say sun shield, I do not mean a simple shade. I mean one of the most remarkable pieces of engineering ever created. The sun shield is made of 5 layers of a material called captain, each layer thinner than a human hair. It is about the size of a tennis court, approximately 21 meters by 14 meters. When fully deployed, it blocks the heat from the sun, the earth, and the moon, creating an enormous shadow in which the telescope sits in perpetual, frigid darkness. The temperature difference between the sun-facing side of the sun shield and the cold side is staggering. The hot side reaches about 85 degrees Celsius, hot enough to boil water. The cold side reaches minus 233 degrees Celsius, cold enough to liquefy nitrogen. This temperature gradient exists across a structure thinner than a sheet of paper, separated by vacuum, and it works. Now, where do you put a telescope like this? You cannot put it in low Earth orbit like Hubble, because the Earth itself is a massive source of infrared radiation, and the telescope would be constantly moving in and out of Earth's shadow, cycling between hot and cold. You need somewhere stable, somewhere cold, somewhere the sun, Earth, and Moon are all on one side so the sunshield can block them all simultaneously. The answer is a place called L2, the second Sun-Earth Lagrange point. Lagrange points are special positions in space where the gravitational forces of the Sun and Earth, combined with the centrifugal force of orbital motion, create a point of relative stability. There are 5 such points, labeled L1 through L5. L2 is located approximately 1.5 million kilometers from Earth, on the side of Earth opposite the Sun. At L2, an object can orbit the Sun at the same rate as Earth, staying permanently behind Earth relative to the Sun. This means that from L2, the Sun, Earth, and Moon are always roughly in the same direction, and the sunshield can block all 3 simultaneously. It is the perfect parking spot for an infrared telescope. Webb does not sit exactly at L2, but orbits around it in what is called a halo orbit, a large, slow loop around the L2 point. This orbit requires occasional small thruster burns to maintain, and it is these thruster burns that ultimately limit Webb's lifetime. The telescope carries a finite amount of fuel, and once it runs out, it can no longer maintain its orbit. The original mission design called for at least 10 years of operation. But here is a wonderful piece of good news. The Ariane 5 rocket that launched Webb on Christmas Day 2021 performed so precisely that very little fuel was needed for the initial trajectory correction. This means Webb has far more fuel remaining than planned, and current estimates suggest the telescope could potentially operate for 20 years or more. We may have this golden eye in the sky until the 2040s. Webb carries 4 main scientific instruments, and each one is a marvel in its own right. NIRCam, the near-infrared camera, is the telescope's primary imaging instrument. It sees in wavelengths from 0.6 to 5 microns, and is responsible for the stunning deep-field images that have captivated the world. NIR-SPEC, the near-infrared spectrograph, is perhaps the most scientifically powerful instrument on board. It can split the light from distant objects into a spectrum, a rainbow of wavelengths, allowing astronomers to determine the chemical composition, temperature, density, and velocity of those objects. Astonishingly, NIR-SPEC can observe up to 100 objects simultaneously using an array of tiny shutters that can be opened and closed individually. MIRI, the mid-infrared instrument, sees in longer wavelengths from 5 to 28 microns, and is the only instrument that requires active cooling beyond what the sunshield provides. MIRI has its own cryocooler that chills it to just 7 Kelvin, a mere 7 degrees above absolute zero. This allows MIRI to see cooler objects, dusty regions, and more distant galaxies than the other instruments. Finally, FGS/NIRISS, the fine guidance sensor and near-infrared imager and slitless spectrograph, provided by the Canadian Space Agency, serves a dual role. It keeps the telescope pointed with extraordinary precision, and it can perform specialized observations such as transit spectroscopy of exoplanet atmospheres. Together, these 4 instruments give Webb an unprecedented view of the infrared universe, from nearby planets in our own solar system to the most distant galaxies at the very edge of the observable universe. On Christmas Day 2021, the Ariane 5 rocket carrying the James Webb Space Telescope lifted off from the Guiana Space Center in Kourou, French Guiana. The world watched with a mixture of awe and terror, The telescope was the product of 30 years of development, the collaboration of over 10,000 scientists and engineers, and a final price tag of approximately $10 billion. And here is what made the launch so terrifying. Webb had 344 single points of failure, 344 things that had to go right, any one of which, if it failed, would have doomed the entire mission. The sunshield had to unfold perfectly. The mirror segments had to deploy correctly. The secondary mirror had to extend on its boom. The solar panel had to deploy. The communications antenna had to orient. Hundreds of latches, releases, motors, hinges, and mechanisms all had to work, in sequence, in the vacuum of space, at temperatures that would shatter most materials, 1 million miles from Earth, where no astronaut could ever reach to fix a mistake. Unlike Hubble, which orbits just a few hundred miles above Earth and was famously repaired by space shuttle astronauts after its flawed mirror was discovered, Webb is so far away that repair is impossible. If anything went wrong, the $10 billion telescope would become the most expensive piece of space debris in human history. Every single deployment step worked perfectly. Every latch released. Every hinge swung. Every motor turned. Every segment aligned. It was one of the most flawless engineering achievements in the history of the human species. And when the first images came back, when the first photons from the distant universe hit that golden mirror and were focused through those extraordinary instruments, the world realized that the gamble had paid off beyond anyone's wildest dreams. Now, before we dive into the specific discoveries, I need to set the stage. I need to explain what the observable universe actually is, because the title of this video asks what Webb has discovered beyond the edge of the universe, and to understand that, you need to understand what the edge is and what it is not. This is where things get genuinely mind-bending, so stay with me, because once you understand this, everything else will make much more sense. The observable universe is not the entire universe. This is one of the most common misconceptions in all of science. When astronomers talk about the observable universe, they are talking about a specific, well-defined region of space. It is the region from which light has had time to reach us since the Big Bang, 13.8 billion years ago. Because light travels at a finite speed, and the universe has a finite age, there is a maximum distance from which we can receive light. That defines the boundary of the observable universe. Now, here is where it gets confusing. You might think the observable universe has a radius of 13.8 billion light-years. Since the universe is 13.8 billion years old, and light travels at 1 light-year per year. But that is wrong. The actual radius of the observable universe is about 46.5 billion light-years. How is that possible? How can we see objects 46.5 billion light-years away if the universe is only 13.8 billion years old? The answer is expansion. Remember, space itself is expanding. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us. The light has been traveling toward us for 13 billion years, but during that time, the space between us and that galaxy has been stretching. The galaxy has been carried farther and farther away by the expansion of space. So by the time the light arrives, the galaxy is no longer 13 billion light-years away. It is much farther. The current distance to the objects whose light is just now reaching us from the very early universe is about 46.5 billion light-years. This means the observable universe is a sphere with a diameter of about 93 billion light-years, centered on us. And here's an important point. There's nothing special about our position. Every observer, everywhere in the universe, has their own observable universe, a sphere centered on them, defined by how far light has traveled from their location since the Big Bang. An alien astronomer in a galaxy billions of light years from us would have their own observable universe, overlapping with ours but not identical. Some of the galaxies they can see, we cannot, and some of the galaxies we can see, they cannot. Within our observable universe, there are approximately 2 trillion galaxies. 2 trillion, that is 2,000 billion. Each of those galaxies contains anywhere from a few million to several trillion stars. Each of those stars may have planets. The total number of stars in the observable universe is estimated to be around 200 billion trillion. That is a 2 followed by 23 zeros. And each of those stars is a nuclear furnace, fusing hydrogen into helium, helium into carbon, carbon into oxygen, steadily building up the periodic table of elements that make up everything we see around us, including our own bodies. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in the hearts of ancient stars that exploded billions of years ago, scattering their elemental guts across space, where they eventually coalesced into new stars, new planets, and eventually into you. You are, quite literally, made of star stuff, as Carl Sagan so beautifully put it. And the James Webb Space Telescope is looking back to the era when the very first of those stars were born. Now, the observable universe has a boundary, but it is not the kind of boundary you might imagine. It is not a wall, it is not a fence, it is not a physical barrier of any kind, it is a horizon. Think of it like the horizon on Earth. When you stand on a flat plane and look into the distance, you can see only so far before the curvature of the Earth hides everything beyond. But you know, intellectually, that there is more land beyond the horizon. It does not end. You just cannot see it from where you are standing. The edge of the observable universe is exactly like that. Except, instead of the curvature of the Earth limiting your view, it is the age of the universe and the finite speed of light. Beyond the observable universe, there is almost certainly more universe, more space, more galaxies, more stars, more of the same cosmic structure that we see within our observable bubble. But the light from those regions has not had time to reach us yet. And here is the cruel twist. Because the expansion of the universe is accelerating, driven by the mysterious force we call dark energy, some of those regions will never be visible to us. Their light will never reach us, no matter how long we wait, because the space between us is expanding faster than light can cross it. They are forever beyond our cosmic horizon, receding into the darkness, lost to us for all eternity. This is not a failure of our technology. This is a fundamental feature of the universe itself. There are parts of reality that are, in principle, forever unknowable. But JWST is pushing us closer to that horizon than we have ever been. And what it has found there has been nothing short of revolutionary. Let me tell you about the most distant galaxy ever discovered. In January 2026, NASA announced a discovery that sent shockwaves through the astronomical community. The James Webb Space Telescope had confirmed the existence of a galaxy called MOM-Z14, and it was the most distant galaxy ever observed by human instruments. The name may sound technical, but let me unpack what it means. The Z14 part refers to its redshift. Redshift, as I explained earlier, is a measure of how much the light from an object has been stretched by the expansion of the universe. The higher the redshift, the more the light has been stretched, which means the farther away the object is and the earlier in cosmic history we are seeing it. A redshift of Z equals 14.4 means that the light from MOM-Z14 has been stretched by a factor of about 15.4. The wavelength of every photon from this galaxy is now more than 15 times longer than when it was emitted. Light that was once ultraviolet is now deep infrared. Only a telescope like JWST, with its exquisite infrared sensitivity, could possibly detect it. And what does a redshift of 14.4 correspond to in terms of cosmic time? It means we are seeing this galaxy as it existed just 280 million years after the Big Bang. Let me put that in perspective. The universe is 13.8 billion years old. 280 million years is just 2% of the total age of the universe. If the entire history of the cosmos were compressed into a single calendar year, with the Big Bang on January 1st and today on December 31st, then MOM-Z14 existed on January 7th. We are seeing a galaxy from the first week of cosmic existence. A galaxy that formed when the universe was a newborn baby, barely distinguishable from the primordial chaos of the Big Bang itself. In terms of light travel distance, MOM-Z14 is 13.5 billion light-years away. The light we are detecting from it has been traveling across the universe for 13.5 billion years, passing through expanding space, getting stretched redder and redder, until it finally arrived at the golden mirror of JWST, carrying with it a message from the dawn of time. But here is where it gets truly bizarre. MOM-Z14 should not exist. At least, not according to our models. The galaxy is far too bright and far too massive for its age. Remember, 280 million years after the Big Bang is an incredibly short time in cosmic terms. The first stars are thought to have formed perhaps 100 to 200 million years after the Big Bang. So MOM-Z14 existed at a time when the universe had only had stars for maybe 80 to 180 million years, at most. That is not enough time, according to standard models, for a galaxy of this brightness and size to have assembled. It is not enough time for enough stars to have formed, lived, died, and enriched the interstellar medium with heavy elements. And yet, JWST's spectroscopic analysis of MOM-Z14 revealed something stunning. It detected nitrogen in the galaxy's spectrum. Nitrogen. Now, you might wonder why nitrogen is significant. Nitrogen is not produced in the Big Bang. The Big Bang produced hydrogen, helium, and tiny traces of lithium and deuterium. That is it. Every other element in the periodic table was produced later, inside stars, through nuclear fusion, or in the catastrophic explosions of dying stars, supernovae. Nitrogen, in particular, is produced through what is called the CNO cycle, a nuclear fusion process that occurs in stars more massive than the Sun. But here is the catch. The CNO cycle requires carbon and oxygen to already be present, which means at least one previous generation of stars must have lived and died, producing those elements, before the stars that made the nitrogen could even begin the process. So the presence of nitrogen in MOM-Z14 means that this galaxy, just 280 million years after the Big Bang, had already gone through at least 2 generations of stars. Stars had formed, burned through their fuel, exploded as supernovae, scattered their heavy elements into space, and then new stars had formed from that enriched material and begun producing nitrogen. All of this had to happen in less than 280 million years. According to our standard models of star formation and evolution, this is extraordinarily difficult, if not impossible. The timescales just do not work. Stars take time to form. They take time to burn through their fuel. Massive stars live fast and die young, perhaps in a few million years. But even with the most generous assumptions, squeezing 2 full generations of stars into 280 million years is a severe challenge. So, what is going on? There are several possibilities, and each one is more fascinating than the last. The first possibility is that star formation in the very early universe was radically different from what we observe today. Perhaps the first stars, the so-called population 3 stars, were far more massive than any stars that exist in the modern universe. Theoretical models suggest that the first stars could have been hundreds or even thousands of times the mass of our Sun. Stars that massive burn through their fuel incredibly quickly, in just a few million years, and when they die, they explode as enormously powerful supernovae called pair instability supernovae, which can scatter heavy elements across vast regions of space. If the first generation of stars was indeed populated by these supermassive monsters, then the enrichment process could have happened much faster than standard models assume. The heavy elements would have been produced quickly, dispersed quickly, and the second generation of stars could have formed and begun producing nitrogen within the tight timescale allowed. The second possibility is even more exotic. Some of the light from MOM-Z14 might not be coming from stars at all. It might be coming from an accreting black hole, an active galactic nucleus at the heart of the galaxy, where matter is falling into a supermassive black hole and releasing enormous amounts of energy. If MOM-Z14 harbors an early supermassive black hole, its accretion radiation could boost the galaxy's apparent brightness far beyond what the stars alone would produce, making the galaxy appear more massive and more evolved than it actually is. The third possibility is the most mind-bending of all, and we will explore it in depth later. Some of the objects we see in the very early universe might not be galaxies at all. They might be what physicists call dark stars, hypothetical stellar objects powered not by nuclear fusion, but by the annihilation of dark matter particles in their cores. But we will get to that. For now, the key takeaway is that MOM-Z14 represents a direct challenge to our understanding of how the universe built its first structures. Something happened in the first 280 million years of cosmic history that was far more violent, far more efficient, and far more rapid than anything our models predicted. And JWST is only beginning to unravel what that something was. MOM-Z14 did not appear out of nowhere. It was the latest in a series of increasingly distant galaxy discoveries by JWST that had been pushing the boundaries of the observable universe further and further back. Before MOM-Z14, the record holder was JADES-GS-Z14-O, a galaxy at redshift Z equals approximately 14.32, corresponding to about 290 million years after the Big Bang. That galaxy was discovered in 2024 and confirmed through extensive spectroscopic analysis. It was already extraordinary, measuring about 1,600 light-years in diameter, and shining with a luminosity that far exceeded expectations. Before JADES-GS-Z14-0, the record was held by JADES-GS-Z13-0 at a redshift of about 13, corresponding to roughly 325 million years after the Big Bang. And before that, there was GN-Z11, discovered by the Hubble Space Telescope at a redshift of about 11, which held the record for years as the most distant known galaxy. Each of these discoveries pushed our observational frontier deeper into the past, but MOM-Z14 stands apart because of the nitrogen detection, which provides not just a distance record but a chemical fingerprint that tells us about the conditions in the very early universe. Each successive discovery is like peeling back another layer of cosmic time, revealing an earlier and earlier chapter in the story of the universe, and each layer reveals something surprising, something that does not quite match our predictions, something that forces us to rethink and revise. The discovery of MOM-Z14 was made possible by a combination of JWST's instruments and a cosmic phenomenon that acts as a natural magnifying glass. That phenomenon is called gravitational lensing, and it is one of the most beautiful and useful predictions of Einstein's general theory of relativity. Einstein's theory tells us that mass warps the fabric of spacetime. A massive object, like a galaxy cluster, creates a curvature in spacetime around it, and that curvature bends the path of light traveling near it. If a massive galaxy cluster sits between us and a more distant galaxy, the cluster's gravity can bend and focus the light from the distant galaxy, amplifying it, making it appear brighter and larger than it would otherwise be. In effect, the galaxy cluster acts as a cosmic magnifying glass, or a gravitational lens. Without gravitational lensing, many of the most distant galaxies detected by JWST would be far too faint to observe. Even with JWST's extraordinary sensitivity, the universe itself is providing us with natural telescopes, giant clusters of dark matter and galaxies that bend and amplify the ancient light from the cosmic dawn, allowing us to peer deeper into the past than our technology alone would permit. It is as if the universe wants to be understood, as if it is collaborating with us in the act of discovery. Now, MOM-Z14 was not the only surprise waiting in JWST's data. When the telescope first began operations in mid-2022 and its first deep-field images started coming in, astronomers were immediately struck by something deeply unsettling. There were too many galaxies. Not just slightly more than expected, dramatically more. And not just more galaxies, but galaxies that were far too massive, far too bright, and far too mature for the age of the universe at which they existed. The standard model of cosmology, known as lambda-CDM, the lambda cold dark matter model, makes very specific predictions about how galaxies form. According to lambda-CDM, galaxy formation is a hierarchical process. Small structures form first. Tiny clumps of dark matter pull into regular matter, which collapses into small protogalaxies. Over time, these small protogalaxies merge with each other, gradually building up into larger and larger structures. The first galaxies should have been small, faint, irregular, and primitive. They should not have been bright, massive, and structured. But that is exactly what JWST found. In deep field survey after deep field survey, JWST revealed galaxies at redshifts of 10 and above, corresponding to less than 500 million years after the Big Bang, that looked far more mature than they had any right to be. Some appeared to contain billions of solar masses worth of stars. Some showed signs of organized structure, with disks and even spiral features. Some were shining with a luminosity that, if interpreted as purely stellar, would require more stellar mass than there was available baryonic matter to form them. The implications were staggering. Headlines around the world declared that JWST had discovered galaxies that should not exist, that the standard model of cosmology was in crisis, that the Big Bang theory itself might need to be revised. But science is a process of careful investigation, not headline-driven panic, and the story is more nuanced than the initial shock suggested. Let me take you through what actually happened, step by step, because the resolution of the impossible galaxy problem is itself one of the most fascinating scientific stories of recent years. When astronomers first analyzed JWST's early images, they estimated the masses of distant galaxies by measuring their brightness and colors and comparing those measurements to theoretical models of stellar populations. The basic logic was straightforward. A galaxy that emits a certain amount of light at certain wavelengths contains a certain number of stars of certain types, which correspond to a certain total stellar mass. This is how galaxy masses are estimated even in the nearby universe. It is a well-established technique. but it relies on assumptions about the types of stars present, their ages, and the ratio of different types of stars to each other. A distribution called the initial mass function, or IMF. In the nearby universe, the IMF appears to be remarkably consistent. It follows a pattern discovered by astronomer Edwin Salpeter in 1955, with many small, faint stars and fewer large, bright stars. But in the very early universe, conditions were drastically different. There were no heavy elements, no dust, no pre-existing magnetic fields. The gas from which the first stars formed was pristine hydrogen and helium, and the physics of gas collapse in such conditions may have favored the formation of much more massive stars than the Salpeter IMF predicts. If the first stars were, on average, much more massive than stars forming today, then a small number of stars could produce an enormous amount of light, mimicking the brightness of a much larger galaxy. A galaxy with a top-heavy IMF might appear 10 times brighter than a galaxy with the same total stellar mass, but a normal IMF. This means that the masses of early galaxies may have been dramatically overestimated. And there was another factor that the initial analyses did not fully account for: active galactic nuclei. Many galaxies harbor supermassive black holes at their centers, and when those black holes are actively accreting matter, they can outshine the entire galaxy. The light from an active galactic nucleus is not stellar light. It is generated by the gravitational energy of matter falling into the black hole, heating up to millions of degrees as it spirals inward, and radiating across the electromagnetic spectrum with extraordinary intensity. If some of the apparently impossible early galaxies were actually hosting active supermassive black holes, then much of their apparent brightness would be coming from the black hole, not from stars. The total stellar mass of the galaxy would be much lower than originally estimated. And, as we will explore in detail later, JWST has indeed discovered that many early galaxies harbor active supermassive black holes, especially the mysterious objects known as little red dots. A landmark study published in August 2024 reanalyzed many of the supposedly impossible galaxies with more sophisticated models that accounted for these factors. The results were revelatory. Many of the galaxies that had initially appeared to be impossibly massive were actually much less massive than first estimated. Some had their mass estimates reduced by factors of 10 or more. The apparent crisis in cosmology began to ease. Lambda CDM was not broken. The Big Bang Theory was not wrong. What was wrong, or at least incomplete, was our understanding of astrophysics in the early universe. The physics of galaxy formation, star formation, and black hole growth in the first few 100 million years of cosmic history was far more complex, far more dynamic, and far more extreme than our models had assumed. The standard cosmological framework, the large-scale picture of how the universe evolves, survived. But the detailed astrophysics of the early universe, the small-scale picture of how galaxies actually formed and grew, needed major revision. This is how science works at its best. A revolutionary observation appears to break the established model. Scientists investigate, refine their analyses, and discover that the model is mostly correct but needs updating in important ways. The result is not the overthrow of established science, but its deepening and enrichment. We do not know less than before. We know more. We know that the early universe was a far more dynamic and violent place than we imagined, and we know that the processes that built the first galaxies were fundamentally different from the processes that operate today. But not all of the tension has been resolved. While many of the impossible galaxies turned out to be less massive than initially estimated, some remain genuinely puzzling. There are still galaxies at extremely high redshifts that appear to be more massive and more evolved than even the revised models can comfortably explain. The universe is telling us something, and we have not yet fully decoded the message. And this brings us to one of the strangest and most exciting discoveries of the James Webb Space Telescope era, the mystery of the little red dots. If you were to look at a typical JWST deep field image, you would see thousands of galaxies of all shapes, sizes, and colors, stretching from the nearby universe all the way back to the cosmic dawn. Most of these galaxies are recognizable types: spirals, ellipticals, irregulars, interacting pairs, galaxy clusters. But scattered among them, in nearly every deep JWST image, there are objects that do not look like anything astronomers had ever seen before. They are tiny, compact, point-like, and red, not just slightly red, deeply, richly red, with a distinctive color that stands out even among the multitude of other objects in the field. They were quickly given a nickname, Little Red Dots, or LRDs, and they are everywhere. Thousands of them have been discovered in JWST data, and they appear in practically every deep observation the telescope makes. They are not local objects. They are not asteroids or satellites or instrumental artifacts. They are ancient, residing at high redshifts, from a time when the universe was less than 1 billion years old. They represent a population of objects that was completely unknown before JWST. No previous telescope had the infrared sensitivity and resolution to detect them. They are a brand new discovery, a brand new class of cosmic object, and nobody is entirely sure what they are. The mystery of the little red dots has sparked one of the most vibrant and contentious debates in modern astronomy. Multiple theories have been proposed, and new data from JWST is constantly shifting the balance between them. Let me walk you through the leading theories, because each one tells us something profound about the early universe. The first, and currently most widely accepted theory, is that little red dots are compact galaxies harboring rapidly growing supermassive black holes at their centers. In this picture, the LRD is essentially a very young galaxy with an active galactic nucleus, a central black hole that is voraciously accreting matter. The black hole is surrounded by a thick cocoon of gas and dust, which absorbs the shorter wavelength light from the accretion disk and re-emits it at longer wavelengths, giving the object its characteristic red color. A study published in January 2026 described these objects as young black holes, 100 times less massive than previously believed, enshrouded in a cocoon of gas, which they are gradually consuming. This picture explains several features of the LRDs. Their compact size is consistent with the light being dominated by a central point source, the black hole's accretion disk, rather than a spread-out stellar population. Their redness is consistent with heavy dust obscuration, and their abundance in the early universe is consistent with the idea that many early galaxies went through a phase of rapid black hole growth. The second theory is more radical and potentially more revolutionary. In February 2026, a study proposed that little red dots are not galaxies with black holes at all. Instead, they might be the birthplaces of direct collapse black holes, a theoretical type of black hole that forms not from the death of a star, but from the direct gravitational collapse of an enormous cloud of primordial gas. In this scenario, the LRD is essentially a cosmic womb, a dense cloud of hydrogen gas that is collapsing under its own gravity, getting denser and hotter, and on the verge of forming a massive black hole seed without ever going through the stage of being a star. This would be an entirely new mechanism of black hole formation, never before observed, and it could solve one of the biggest puzzles in astrophysics. How did supermassive black holes weighing billions of times the mass of the Sun come to exist when the universe was less than 1 billion years old? If they started from tiny stellar mass seeds, a few tens of solar masses each, there simply was not enough time for them to grow to billions of solar masses through normal accretion. But if they started as direct collapse black hole seeds, weighing tens of thousands to hundreds of thousands of solar masses right from the start, the growth problem becomes much more manageable. A third theory, proposed by researchers at Penn State University in September 2025, suggests that little red dots might be something that has never been seen before in the history of astronomy: black hole star atmospheres. In this picture, a massive black hole is surrounded by a stellar-like envelope of gas, creating a hybrid object that is part black hole, part star. The gas envelope absorbs and re-emits radiation from the accretion process, giving the object a characteristic spectrum and color that matches the observed properties of LRDs. This would represent a completely new phase in the life cycle of cosmic objects, a transitional state between a collapsing gas cloud and a fully fledged supermassive black hole. And there is a fourth possibility, suggested by very recent research in early 2026. Some little red dots might not contain black holes at all. They might be extremely dense clusters of massive stars, so dense and so massive that they are on the verge of gravitational collapse. In this scenario, the stars are so closely packed that the cluster appears as a single point-like source, and the collective light from the stars, possibly including exotic types like Wolf-Rayet stars that have strong spectral features, produces the observed red color. These dense stellar clusters might be the precursors of the direct collapse black holes described in the second theory. First, a dense cluster of massive stars forms. The stars live fast and die young, and when they die, their remnants, possibly including intermediate mass black holes, merge together, eventually creating a supermassive black hole seed. The LRD would then represent a snapshot of this process in action, a moment frozen in time when the stars are still shining, but the collapse into a black hole is imminent. The truth is that little red dots probably are not just one thing. Different LRDs may be explained by different mechanisms. Some may be young galaxies with growing black holes. Some may be direct collapse black hole nurseries. Some may be dense stellar clusters. The population as a whole may represent a range of objects at different stages of a common evolutionary pathway, from gas cloud to stellar cluster, to black hole seed, to active galactic nucleus, to mature galaxy. If this is the case, then little red dots are not just a new type of object. They are a window into the entire process of structure formation in the early universe, a process that has been hidden from us until JWST opened its golden eye and looked back into the cosmic dawn. The implications are staggering. If even a fraction of little red dots are confirmed as direct collapse black hole nurseries, it would mean that the seeds of the supermassive black holes that sit at the centers of virtually every large galaxy in the universe, including the 4 million solar mass black hole at the center of our own Milky Way, were planted not by the gradual growth of stellar remnants over billions of years, but by the rapid, catastrophic collapse of primordial gas clouds in the first few 100 million years of cosmic existence. The monsters that rule the hearts of galaxies today were born in an instant, in a cosmic thunderclap of gravitational collapse that happened before the universe had even learned to make proper stars. That is a profound revision of our cosmic story, and it is one of the most exciting avenues of research that JWST has opened up. And speaking of supermassive black holes in the early universe, this is a good moment to dive deeper into one of JWST's most unsettling discoveries: the existence of black holes that are far too massive, far too early in cosmic history. This is a puzzle that predates JWST. Even before Webb launched, astronomers using ground-based telescopes and the Hubble Space Telescope had discovered quasars, extremely luminous active galactic nuclei powered by supermassive black holes, at very high redshifts. Some of these quasars, shining from a time when the universe was less than 1 billion years old, appeared to be powered by black holes weighing over 1 billion solar masses. This was already a problem. How do you grow a black hole to 1 billion solar masses in less than 1 billion years? The standard picture of black hole growth involves accretion, the process by which a black hole pulls in surrounding gas, which forms a hot disk around the black hole and gradually spirals inward. But accretion has a speed limit. The infalling gas heats up and radiates intensely, and the radiation pressure from this light pushes back against the infalling gas, limiting the rate at which the black hole can grow. This limit is called the Eddington limit, named after the astrophysicist Arthur Eddington. If a black hole accretes at the Eddington limit continuously, without interruption, starting from a stellar mass seed of about 10 to 100 solar masses formed from the death of one of the first stars, it takes roughly 1 billion years to reach 1 billion solar masses. That is cutting it extremely close for the observed high redshift quasars, and it requires perfect conditions. Continuous accretion at the maximum possible rate for the entire time, with no interruptions, no episodes of feedback that shut down accretion, and no mergers that temporarily disrupt the feeding process. In reality, accretion is messy, intermittent, and often disrupted, which means the real growth time should be much longer than the theoretical minimum. JWST has made this problem dramatically worse. By peering deeper into the early universe than any previous telescope, JWST has discovered supermassive black holes at even higher redshifts, existing at even earlier times, and many of them are disproportionately massive compared to their host galaxies. In the local universe, there is a well-established relationship between the mass of a galaxy's central black hole and the mass of the galaxy's stellar bulge. The black hole mass is typically about 0.1% of the bulge mass. This relationship, known as the Magorian relation or the M-sigma relation, suggests a coevolution between galaxies and their central black holes, with the two growing in lockstep over cosmic time. But JWST's observations of the early universe show something very different. The black holes in early galaxies appear to be overmassive, meaning they are much more massive relative to their host galaxies than the local M-sigma relation would predict. In some cases, the black holes are 10 to 100 times more massive relative to their galaxies than expected. This implies that in the early universe, the black holes grew first, and the galaxies grew later, catching up over time. The traditional picture of coevolution, with galaxies and black holes growing together in a balanced dance, may not apply to the earliest epoch of cosmic history. Instead, the early universe may have been dominated by a phase of rapid, aggressive black hole growth, with the galaxies being assembled around and after the black holes. This is a fundamental challenge to our understanding of structure formation and evolution. In November 2025, the European Space Agency reported that JWST had spotted what they called a greedy, supermassive black hole in the early universe, a black hole that was accreting matter at an extraordinary rate, rapidly consuming the gas in its host galaxy. The black hole was overmassive compared to its galaxy's stellar mass, consistent with the pattern of early black hole dominance that JWST has been revealing. And in January 2026, new JWST data confirmed a decade-old theoretical prediction. The first supermassive black holes may have formed through direct collapse, without the intermediate step of stellar death. This confirmation came from analyzing the spectral properties of extremely distant active galactic nuclei and comparing them to predictions from direct collapse black hole formation models. The match was striking. The theoretical predictions, long regarded as speculative, were being vindicated by real data from the real universe. A paper published in February 2026 went further, arguing that many of the little red dots discovered by JWST are actually direct collapse black holes seen in their infancy, still surrounded by the cocoons of gas from which they formed. If this interpretation holds up, it means JWST is literally watching the birth of supermassive black holes, catching them in the act of forming through a process that has never been directly observed before. In July 2025, NASA announced what may be the most dramatic piece of evidence yet. The James Webb Space Telescope observed an object in the very distant universe, in a system nicknamed the Infinity Galaxy, that showed all the hallmarks of a direct collapse black hole. The Infinity Galaxy is actually a pair of colliding galaxies, and at the point where the two galaxies are merging, JWST detected an object with a spectrum consistent with a massive black hole seed that formed directly from collapsing gas, without first becoming a star. The conditions in the merging system, the intense radiation field, the lack of heavy elements in certain regions, the high gas densities, matched the theoretical requirements for direct collapse almost perfectly. The discovery was covered by major outlets, including astronomy.com, which described it as evidence of a direct collapse black hole found in a galaxy collision, a scenario that theorists had predicted but had never been observed. Let me take a step back and help you appreciate just how wild this is. For decades, the question of how supermassive black holes formed was one of the great unsolved mysteries of astrophysics. There were theoretical ideas, clever models, mathematical frameworks, but no observational evidence to distinguish between the competing theories. JWST changed all of that. In just a few years of operation, it has found galaxies with overmassive black holes, little red dots that may be black hole nurseries, and direct collapse black hole candidates. It has opened a window into a cosmic epoch that was previously invisible, and what it has revealed is a universe in which black holes were born not as the small remnants of dead stars but as massive seeds, formed in the catastrophic gravitational collapse of pristine hydrogen gas, growing voraciously from the very beginning, and eventually becoming the supermassive monsters that anchor every galaxy in the cosmos today. If you are a galaxy, your black hole came first. It was there before you. It is your origin, not your companion. That is a revolutionary idea, and it is one that JWST has brought to the threshold of confirmation. Now, I want to take you somewhere even more exotic. I want to tell you about dark stars. Not dark in the sense of being invisible, and not dark in the sense of being made entirely of dark matter. Dark stars are a theoretical type of stellar object, first proposed in 2007 by physicist Catherine Freese and her colleagues. That would have been powered not by the nuclear fusion that powers every star we know of today, but by the annihilation of dark matter particles in their cores. To understand dark stars, you need to understand a bit about dark matter. Dark matter makes up approximately 27% of the total mass-energy content of the universe. Regular matter, the stuff that makes up stars, planets, and people, accounts for only about 5%. The remaining 68% is dark energy, the mysterious force driving the accelerating expansion of the universe. Dark matter does not emit, absorb, or reflect light. It is completely invisible. We know it exists because of its gravitational effects on visible matter. Galaxies rotate faster than they should if they were made only of visible matter, which means there must be additional, invisible mass providing extra gravitational pull. Galaxy clusters contain far more mass than the visible galaxies within them, as revealed by gravitational lensing. And the large-scale structure of the universe, the cosmic web of filaments and voids, matches predictions only if dark matter is included. We know dark matter is there, we just do not know what it is. One of the leading candidates for the dark matter particle is a hypothetical particle called a WIMP, a weakly interacting massive particle. WIMPs would interact with each other and with regular matter through gravity and through the weak nuclear force, but not through electromagnetism or the strong nuclear force, which is why they are invisible and pass through ordinary matter like ghosts. Now, if WIMPs are their own antiparticle, which many theoretical models predict, then when two WIMPs meet, they can annihilate each other, converting their mass into energy. In the modern universe, dark matter is spread out thinly, and WIMP annihilation events would be rare. But in the early universe, dark matter was much denser. And at the centers of the very first dark matter halos, the clumps of dark matter that would eventually host galaxies, the density was extremely high. Catherine Freese's idea was this. When the first gas clouds began to collapse under gravity to form the very first stars, they were collapsing inside dark matter halos. The dark matter at the center of these halos was so dense that WIMP annihilation was occurring at a significant rate, producing a steady stream of energy that heated the gas cloud from the inside. This dark matter heating would have prevented the gas from collapsing all the way down to the densities needed to ignite nuclear fusion. Instead of forming a compact, hot, fusion-powered star, the gas would have formed something very different. A large, puffy, relatively cool, but extraordinarily luminous object, powered by the continuous annihilation of dark matter particles in its core. These are dark stars. Dark stars would have been unlike anything that exists in the modern universe. They could have been millions of times the mass of the Sun, enormous bloated objects with radii comparable to entire star-forming regions. They would have been relatively cool at their surfaces, perhaps only around 10,000 Kelvin, comparable to a hot normal star, but their sheer size would have made them incredibly bright. A single dark star could have shone with the luminosity of an entire galaxy. And here is the connection to JWST's observations. Some of the objects that JWST has detected at the highest redshifts, objects that we have been interpreting as galaxies, might actually be individual dark stars. A single supermassive dark star could produce enough light to mimic an entire early galaxy, which would explain why some of these objects appear too bright and too mature for their age. They are not galaxies with billions of stars. They are single enormous objects powered by dark matter. In 2023, the first 3 candidate dark stars were identified in JWST data from the JADES survey. These objects had properties consistent with theoretical dark star predictions. Unusually luminous, unusually cool for their luminosity, and compact. Then, in October 2025, more dark star candidates were found at even higher redshifts, corresponding to just 300 million years after the Big Bang. Catherine Freese, now at the University of Texas at Austin, stated, "For the first time, we have identified spectroscopic supermassive dark star candidates in JWST, including the earliest objects at redshift 14, only 300 million years after the Big Bang. The evidence is still circumstantial. These objects could be explained by other phenomena, such as unusual galaxies or active galactic nuclei with unusual properties. But the fact that their properties match dark star predictions across multiple observational features is intriguing. And if dark stars are confirmed, the implications are enormous. First, it would be the first observational evidence for the WIMP model of dark matter. We have been searching for WIMPs in underground detectors, in particle accelerators, and through astronomical observations for decades. And so far, we have found nothing. Dark stars would provide an entirely new and unexpected way to detect dark matter's presence. Second, dark stars would represent a completely new category of astrophysical object. one that exists only in the earliest epoch of cosmic history, before normal star formation took over. They would be the universe's first lights, predating even the first fusion-powered stars. Third, dark stars could help solve the impossible galaxy problem. If some of the apparently massive early galaxies are actually individual dark stars, then the total stellar mass in the early universe would be much lower than JWST data initially seemed to suggest, reducing the tension with lambda CDM predictions. And fourth, when a dark star eventually exhausted its dark matter fuel, it would collapse. The question is, what would it collapse into? One possibility is that a supermassive dark star, weighing millions of solar masses, would collapse directly into a supermassive black hole, without ever going through a fusion-powered stellar phase. This would provide yet another pathway to the formation of early supermassive black holes, complementing the direct collapse mechanism. Dark stars and direct collapse black holes might be two aspects of the same story. The story of how the universe built its first massive structures through mechanisms that are entirely different from anything that happens in the cosmos today. Let me now take you to one of the most beautiful chapters in the story of the early universe, the epoch of ionization. This is the universe's coming-of-age story, the moment when the cosmos transformed from a dark, opaque fog into the transparent, star-filled expanse we see today. Understanding reionization is crucial to understanding what JWST has discovered beyond the edge, because reionization defines the boundary between the universe we can observe and the universe that remains hidden. Here is the story. After the Big Bang, the universe was a hot, dense plasma of subatomic particles. Over the first 380,000 years, it cooled and expanded, and eventually the temperature dropped low enough for electrons and protons to combine and form neutral hydrogen atoms. This event is called recombination, which is a somewhat misleading name because it implies the atoms were combined before and are recombining, when in fact they were combining for the first time. But the name has stuck. When recombination occurred, the universe became transparent to light for the first time. Photons that had been bouncing around in the plasma were suddenly free to travel in straight lines across the cosmos. Those photons are still traveling today, and they make up the cosmic microwave background radiation, the oldest light in the universe, the faint afterglow of the Big Bang that fills every corner of the sky. After recombination, the universe entered the Dark Ages. There were no stars, no galaxies, no sources of visible light, just vast clouds of neutral hydrogen gas, slowly cooling and slowly being pulled together by the gravity of dark matter into ever denser clumps. For perhaps 100 to 200 million years, the universe was utterly dark. Then, slowly, in the densest regions, where dark matter had accumulated the most matter, the first stars began to form. These first stars were hot, massive, and luminous, and they emitted intense ultraviolet radiation. This ultraviolet radiation was energetic enough to strip electrons away from hydrogen atoms, ionizing them. Each star created a bubble of ionized hydrogen around itself, a region of transparent space in the otherwise opaque fog of neutral hydrogen. As more and more stars formed, and as the first galaxies assembled, the bubbles grew larger and began to overlap. The fog was being cleared, one bubble at a time. This process is the epoch of reionization, and it took hundreds of millions of years to complete. By about 1 billion years after the Big Bang, the fog had been almost entirely cleared, and the universe was once again transparent, this time permanently. The epoch of reionization is the cosmic transition from darkness to light, from opacity to transparency, from the Dark Ages to the luminous universe we inhabit today. JWST was specifically designed to study this transition, and it has delivered beyond anyone's expectations. In March 2025, a team of astronomers using JWST announced the discovery of a galaxy called JADES-GS-Z13-1, observed at a time just 330 million years after the Big Bang. This galaxy was remarkable not just for its extreme distance, but for what it revealed about the process of reionization. JWST's spectroscopic data showed that this galaxy had created an ionized bubble around itself, a region of transparent space surrounded by the opaque fog of neutral hydrogen. It was the earliest direct evidence of reionization in action. Scientists could literally see the galaxy clearing the fog around it, punching a hole in the cosmic darkness with its ultraviolet light. The discovery confirmed that reionization began extremely early, earlier than many models had predicted, and that even tiny young galaxies were capable of contributing to the process. As the team behind the discovery described it, this galaxy was mysteriously clearing the fog of the early universe. The question of what drove reionization is still being debated, and JWST is providing critical new data. The traditional view was that young, star-forming galaxies were the primary drivers, producing enough ultraviolet photons to ionize the intergalactic medium. But JWST has revealed that the situation is more complex. Active galactic nuclei, the luminous black holes at the centers of early galaxies, also produce copious ultraviolet radiation, and the discovery of abundant little red dots suggests that active black holes were far more common in the early universe than previously realized. Some of that radiation would have escaped the galaxies and contributed to ionizing the surrounding hydrogen. Dark stars, if they existed, would also have contributed, producing enormous amounts of ionizing radiation from their bloated surfaces. The emerging picture is one of collaboration. Stars, black holes, and possibly exotic objects all working together to clear the cosmic fog, each contributing according to its nature and abundance. The epoch of reionization was not a single event driven by a single cause. It was a complex, drawn-out process driven by the collective action of every source of ultraviolet light in the young universe. In December 2025, JWST made another stunning discovery related to this epoch. It detected a supernova at an unprecedented distance in the early universe, tied to a long-duration gamma-ray burst. This observation was the direct detection of a massive star dying in the era of reionization. A star whose violent death scattered heavy elements into the surrounding space and contributed to the enrichment of the interstellar medium. Supernovae in the early universe served multiple roles. They produced the heavy elements necessary for the formation of rocky planets and, ultimately, life. They injected energy into the surrounding gas, driving turbulence and shaping the structure of early galaxies, and their radiation contributed to the ionization of the intergalactic medium. This single observed supernova was a window into the violent, creative chaos of the cosmic dawn, a time when the universe was simultaneously destroying and creating, tearing apart old structures and building new ones, in a frenzy of activity that would eventually produce the relatively calm and ordered cosmos we see today. Now, let us shift our focus from the very distant universe to something closer to home, but equally profound. Let me tell you about the Hubble tension, because this is arguably the most important scientific controversy of our time, and JWST is right in the middle of it. The Hubble tension is a disagreement between two different measurements of the rate at which the universe is expanding, and if the disagreement is real, it could mean that our fundamental understanding of the cosmos is wrong. Here is the background. In 1929, Edwin Hubble made one of the most important discoveries in the history of science. By observing the relationship between the distances of galaxies and the speeds at which they are moving away from us, he discovered that the universe is expanding. The farther away a galaxy is, the faster it is receding, following a simple linear relationship. The constant of proportionality in this relationship is called the Hubble constant, denoted h0, and it describes the current rate of expansion of the universe. Measuring h0 accurately is one of the most important tasks in all of cosmology, because the expansion rate determines the age, size, and ultimate fate of the universe. Over the decades, astronomers have developed increasingly sophisticated methods for measuring h0, and these methods fall into two broad categories. The first category involves measuring the expansion rate directly, using objects in the nearby universe as distance markers. The most important of these distance markers are Cepheid variable stars, stars whose brightness pulsates in a regular pattern, with the period of pulsation directly related to the star's intrinsic luminosity. By measuring the period of a Cepheid's pulsation, astronomers can determine how bright the star actually is, and by comparing that to how bright it appears, they can determine how far away it is. Cepheids are used to calibrate other distance measurement techniques, such as Type 1a supernovae, forming a chain of overlapping methods called the cosmic distance ladder that extends from nearby galaxies to billions of light-years away. Using this approach, the SHOES collaboration, led by Nobel laureate Adam Rice, has measured h0 to be approximately 73 to 74 kilometers per second per megaparsec. The second category involves measuring the expansion rate indirectly, using observations of the very early universe. The cosmic microwave background, the ancient light from 380,000 years after the Big Bang, contains tiny temperature fluctuations that encode detailed information about the composition, geometry, and expansion history of the universe. By analyzing these fluctuations with the lambda-CDM model, cosmologists can predict what the current expansion rate should be. The Planck satellite, which mapped the CMB with extraordinary precision, derived a value of h0 of approximately 67.4 kilometers per second per megaparsec. Here's the problem. 73 to 74 is not the same as 67.4. The difference may seem small in absolute terms, about 6 to 7 kilometers per second per megaparsec, but it is statistically enormous. The measurement uncertainties are now so small that the discrepancy exceeds 5 sigma, meaning there is less than a 1 in 3.5 million chance that the disagreement is due to random measurement error. In statistical terms, 5 sigma is the gold standard for claiming a discovery. If a particle physics experiment at CERN found a new particle at 5 sigma, it would be hailed as a definitive discovery. The Hubble tension has reached that level of statistical significance, and yet it remains a disagreement between two measurements, not a new discovery, because nobody knows what is causing it. JWST entered this arena with the promise of potentially resolving the tension. One of the key concerns about the local measurement of h0 using Cepheid stars was that Hubble Space Telescope images of distant Cepheids might be contaminated by crowding. In crowded star fields, the light from a Cepheid could be blended with the light from nearby, unresolved stars, making the Cepheid appear brighter than it actually is, and thus introducing a systematic bias into the distance measurement. JWST, with its vastly superior infrared resolution, could observe the same Cepheids with much less crowding, providing an independent check on Hubble's measurements. In December 2024, the results of JWST's largest study of the universe's expansion rate were published, and they confirmed the Hubble tension. JWST's observations of Cepheid stars showed that Hubble's measurements were not significantly contaminated by crowding. The local value of h0 remained high, around 73 to 74, and the disagreement with the Planck CMB value persisted. The tension was real, and it was not going away. In December 2025, the Keck Observatory added another data point, further sharpening the local measurement and deepening the tension. The universe, it seemed, was expanding faster than it should be, according to our best model of cosmology. So, what could be causing the Hubble tension? There are several possibilities, each of which would have profound implications for our understanding of the universe. The first possibility, and the one that many astronomers initially favored, is that there is a systematic error in one or both measurements. Perhaps the Cepheid distance ladder has an unaccounted-for bias. Perhaps the CMB analysis is sensitive to some unknown foreground contamination. But as measurements have improved and been cross-checked with multiple independent techniques, including JWST, the room for systematic errors has shrunk dramatically. It is becoming increasingly difficult to blame the tension on measurement mistakes. The second possibility is that our cosmological model is incomplete. Lambda CDM assumes that the universe contains ordinary matter, cold, dark matter, and dark energy with a constant energy density, described by a cosmological constant lambda. It assumes that general relativity is the correct theory of gravity on all scales, and it assumes that the physics of the early universe is well understood. If any of these assumptions is wrong, the predicted value of H0 from the CMB would be different, potentially resolving the tension. One specific proposal is called early dark energy. This idea suggests that there was an additional component of dark energy that was active in the early universe, before recombination, but then decayed away, leaving no direct trace in the CMB, but subtly altering the expansion history in a way that changes the predicted value of H0. Early dark energy models can potentially resolve the Hubble tension, but they introduce new parameters and new complications, and they are not yet widely accepted. The third possibility is new particle physics. The CMB analysis assumes a specific number of particle species in the early universe, primarily the three known types of neutrinos. If there were additional light particles, sometimes called dark radiation or sterile neutrinos, they would have altered the expansion rate of the early universe, changing the predicted H0. This is a testable hypothesis, and experiments searching for evidence of such particles are ongoing. The fourth possibility is that general relativity itself might need modification at cosmological scales. This is the most radical option, and it is taken seriously by a minority of physicists. Modified gravity theories, such as extensions of general relativity that include additional fields or higher-order terms, can alter the expansion history of the universe in ways that might resolve the tension. But modifying general relativity is dangerous territory, because Einstein's theory has been confirmed to extraordinary precision in every other context, from the orbits of planets to the emission of gravitational waves from merging black holes. Any modification must preserve all of these successes while also changing the cosmological expansion rate. That is an extremely tight constraint. The fifth possibility is that we live in a local void, a region of space that is slightly less dense than the cosmic average. In a void, the local expansion rate would be faster than the global average, because there is less matter to slow the expansion. If our local neighborhood is underdense by the right amount, it could explain why the locally measured H0 is higher than the CMB predicted global value. Some studies have found evidence for such a local void, but others have not, and the required underdensity is larger than what most surveys suggest. The honest answer is that we do not know what is causing the Hubble tension. It could be any of these possibilities, or it could be something completely unexpected. What we do know is that the tension is real, it is statistically significant, and it is not going away. And this is actually exciting. When measurements disagree at this level, It usually means we are on the verge of discovering something new about the universe. The last time we had a similar crisis in cosmology, it was the discovery in 1998 that the expansion of the universe is accelerating, which led to the discovery of dark energy, one of the most profound revelations in the history of physics. The Hubble tension might be pointing us toward an equally profound discovery. We just do not know what it is yet. And JWST, by providing the most precise measurements of cosmic distances ever achieved, is playing a central role in this unfolding scientific drama. Now, let us talk about something that JWST has revealed that is, in many ways, the most spectacular visualization of the cosmic structure ever produced: the mapping of dark matter. I told you earlier that dark matter makes up about 27% of the universe's mass-energy content. I told you that it is invisible, detectable only through its gravitational effects. But what I have not yet told you is what dark matter looks like, how it is distributed, and how it shapes the universe on the largest scales. And thanks to JWST, we now have the most detailed picture of that distribution ever created. In January 2026, a team of researchers using JWST released the most intricate map of cosmic dark matter ever produced. The map was constructed by analyzing the shapes of approximately 250,000 galaxies, looking for subtle distortions caused by gravitational lensing. Remember, dark matter bends light. When light from a distant galaxy passes through a region of space that contains a concentration of dark matter, the dark matter's gravity bends the light, subtly distorting the shape of the background galaxy. By measuring these distortions across hundreds of thousands of galaxies, astronomers can reconstruct the distribution of dark matter in the intervening space, creating a map of the invisible substance that pervades the cosmos. The result was breathtaking. The dark matter map, overlaid on a JWST image containing nearly 800,000 galaxies, revealed the cosmic web in unprecedented detail. The cosmic web is the large-scale structure of the universe. It consists of vast filaments of dark matter, stretching across hundreds of millions of light-years, connecting massive nodes called galaxy clusters. Between the filaments are enormous voids, regions of space that are almost empty, containing very few galaxies. The galaxies we see are not randomly distributed. They are strung along the filaments of the cosmic web, like dewdrops on a spider's web, sitting in the places where dark matter is densest. The cosmic web is the skeleton of the universe, the invisible scaffolding upon which all visible structure is built. The 2026 dark matter map revealed never-before-seen structures in this cosmic web. It showed fine details in the filaments, small-scale fluctuations in the dark matter distribution that had been predicted by simulations but never directly observed. It showed how the dark matter distribution changes with cosmic time, how the filaments grow and evolve as the universe ages. And it provided new constraints on the nature of dark matter itself. One particularly intriguing line of research, highlighted in a December 2025 study from Arizona State University, uses JWST data to test whether dark matter might be composed of ultralight particles called axions. Axions are a theoretical particle originally proposed to solve a problem in particle physics, but they have since become a leading dark matter candidate. If dark matter is made of ultralight axions, their quantum wave-like nature would prevent structures from forming below a certain size scale. Very small dark matter halos, and the tiny galaxies they would host would be smoothed out by quantum effects. By looking at the smallest galaxies and dark matter structures in JWST data, astronomers can test this prediction and potentially determine whether dark matter is made of axions or something else. The result would not just tell us about dark matter, it would tell us about the fundamental nature of matter itself, connecting the largest structures in the universe to the smallest scales of quantum mechanics. The dark matter map also highlights the power of gravitational lensing as a tool, which brings us to one of the most poetic discoveries of the JWST era, the star Earendel. In 2022, the Hubble Space Telescope discovered a single point of light in a dramatically lensed galaxy at very high redshift. The galaxy, known as the Sunrise Arc, was being stretched and magnified by the gravitational lensing of a massive galaxy cluster sitting between it and us. Along the arc, at a point of extreme magnification where the lensing effect was at its maximum, there was a single, unresolved point of light. The astronomers named it Earendel, from the Old English word for morning star. They estimated that it was the most distant individual star ever detected, its light having traveled for approximately 12.9 billion years, from a time when the universe was only about 900 million years old. JWST later observed Earendel with its vastly superior infrared instruments and confirmed its extreme distance. The telescope's analysis suggested that Earendel could be a massive star, more than twice as hot as our Sun, and roughly 1 million times more luminous. But there was a twist. In August 2025, a new analysis raised the possibility that Earendel might not be a single star at all. Given the extreme magnification involved, even a small cluster of stars, tightly bound together, could appear as a single point of light. The debate continues. Whether Earendel is a single extraordinary star or a compact stellar cluster, it remains one of the most distant individual objects ever observed, a beacon of light from the cosmic dawn, visible to us only because the universe's own dark matter, acting as a gravitational lens, chose to magnify it for our instruments to see. There is something profoundly beautiful about that. The invisible substance that makes up most of the universe's mass, the dark matter that we cannot see or touch or taste, is the very thing that bends light and allows us to see farther into the cosmos than we otherwise could. Dark matter is not just a mystery. It is a tool, a cosmic magnifying glass, an accomplice in our quest to understand the universe. And now, let me tell you about something that might be the most emotionally resonant discovery in all of JWST's work. Let me tell you about the search for life beyond Earth. For as long as human beings have looked at the stars, we have wondered whether we are alone. Is Earth the only place in the universe where life exists? Or is life common, scattered across the cosmos on countless worlds we have never seen? For most of human history, this was a philosophical question, not a scientific one. We had no way to detect life on other worlds, no way to analyze the atmospheres of planets orbiting other stars, no way to look for the chemical fingerprints that living organisms leave on their environments. JWST has changed that. For the first time in history, we have an instrument capable of detecting the chemical composition of exoplanet atmospheres, including chemicals that might indicate the presence of biological activity. The technique is called transit spectroscopy. When an exoplanet passes in front of its host star, a tiny fraction of the starlight passes through the planet's atmosphere on its way to our telescopes. Different molecules in the atmosphere absorb different wavelengths of light, leaving a characteristic fingerprint in the spectrum. By analyzing this fingerprint, astronomers can determine which molecules are present in the planet's atmosphere. JWST's infrared sensitivity and spectral resolution make it the most powerful instrument ever built for this purpose. The most dramatic result so far has come from a planet called K2-18b. K2-18b is a sub-Neptune exoplanet, about 8.6 times the mass of Earth, orbiting a red dwarf star 124 light-years from our solar system. It orbits within its star's habitable zone, the range of distances at which liquid water could exist on the planet's surface. Initial JWST observations, published in 2023, detected methane and carbon dioxide in K2-18b's atmosphere. This was already remarkable because the combination of methane and carbon dioxide, in the absence of significant carbon monoxide, is consistent with a planet that has a water ocean beneath a hydrogen-rich atmosphere. Such a planet has been called a Hycean world, a hypothetical type of habitable exoplanet with a global ocean and a thick hydrogen atmosphere. But the most explosive finding was the tentative detection of dimethyl sulfide, or DMS, in K2-18b's atmosphere. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by marine phytoplankton. It is one of the most reliable biosignature gases known, because there are very few non-biological processes that can produce it in significant quantities. If DMS is genuinely present in K2-18b's atmosphere, it would be an extraordinarily strong hint, though not definitive proof, that some form of biological activity is occurring on that world. In April 2025, astronomers at the University of Cambridge reported what they called the strongest hints yet of biological activity outside the solar system, based on refined analysis of the JWST data from K2-18b. The DMS detection was described as more robust than the initial tentative signal, though still not at the level of certainty required for a definitive claim. However, within days, a counter-study raised doubts, arguing that the DMS signal could be an artifact of the data analysis or could have non-biological explanations. The scientific community remains cautious. The detection of DMS on K2-18b is a signal, not a conclusion. More JWST observations are being conducted, and the data is being analyzed by multiple independent teams using different methods. If the signal holds up, it will be one of the most important discoveries in the history of science. If it does not, it will still have demonstrated that JWST has the capability to search for biosignatures on distant worlds, paving the way for future discoveries. Beyond K2-18b, JWST has made significant progress in studying the atmospheres of rocky exoplanets, which are potentially more Earth-like. In December 2025, JWST found the strongest evidence yet for an atmosphere around a rocky exoplanet, a world described as a wet lava ball. A rocky planet with a substantial atmosphere despite orbiting close to its host star. This was important because one of the biggest questions in exoplanet science is whether small rocky planets orbiting red dwarf stars, the most common type of star in the galaxy, can retain their atmospheres. Red dwarf stars are notorious for their violent flares and intense radiation, which can strip the atmospheres from nearby planets. If rocky planets can nonetheless maintain atmospheres, the prospects for life in the galaxy increase enormously, because red dwarf stars make up about 70% of all stars. And then there is the TRAPPIST-1 system, one of the most exciting planetary systems ever discovered. TRAPPIST-1 is a small, cool red dwarf star about 40 light-years from Earth, and it is orbited by 7 Earth-sized rocky planets, several of which lie in the habitable zone. JWST has been studying the TRAPPIST-1 planets extensively, characterizing their atmospheres and searching for signs of habitability. The results so far have been mixed. Some of the planets appear to lack substantial atmospheres, as feared for planets orbiting red dwarf stars. But the observations are ongoing, and the inner planets do not necessarily represent the conditions on the outer ones. TRAPPIST-1e and TRAPPIST-1f, which are within the habitable zone, are prime targets for continued JWST observations. If JWST detects a significant atmosphere on either of these planets, It will be a landmark moment in the search for habitable worlds. Let me be clear about what JWST can and cannot do in the search for life. JWST can detect biosignature gases in exoplanet atmospheres. It can identify molecules like methane, carbon dioxide, water, ozone, and potentially DMS. It can characterize the temperature, pressure, and composition of planetary atmospheres, but it cannot directly image exoplanets or their surfaces. It cannot see oceans, continents, or vegetation, and it cannot definitively prove that life exists because there may be non-biological processes that produce the same chemical signatures. A definitive detection of extraterrestrial life will likely require multiple lines of evidence from multiple instruments and missions, building up a case that is so strong that no non-biological explanation can account for all the data. JWST is the first step in that process, and the fact that it can even take that step, that we have built an instrument capable of sniffing the atmospheres of worlds orbiting other stars, is itself an astonishing achievement. We are the first generation in the history of our species that has the tools to answer the question, are we alone? And now we have arrived at the deepest, most profound question of all. What is beyond the edge? What lies past the boundary of the observable universe, in the darkness that no telescope can penetrate, in the regions of space whose light will never reach us? This is the question that has haunted human minds for as long as we have had minds to haunt, and it is a question that JWST, for all its power, cannot directly answer. The observable universe has a horizon, and that horizon is an absolute limit. No matter how powerful our telescopes become, no matter what wavelengths they observe in, they cannot see beyond the cosmic horizon. Light from those regions has not had time to reach us, and in many cases it never will, because the expansion of the universe carries those regions away from us faster than light can bridge the gap. But the fact that we cannot see beyond the horizon does not mean we know nothing about what is there. Indirect evidence, theoretical reasoning, and mathematical models give us a surprisingly detailed picture of what lies beyond, and the possibilities range from the comforting to the mind-bending to the genuinely terrifying. The simplest and most widely accepted possibility is that beyond the edge of the observable universe, there is simply more universe. More space, more galaxies, more stars, more planets, more of the same cosmic web of matter and dark matter that we see within our observable bubble. This is the prediction of the cosmological principle, the foundational assumption of modern cosmology, which states that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction and from every location. If the cosmological principle holds, then our observable universe is a representative sample of the whole, and the regions beyond our horizon are statistically identical to the regions within it. They contain the same types of galaxies, the same distribution of matter, the same laws of physics. There is nothing special about our location, and there is nothing special about the boundary of our observable universe. It is just a horizon, and beyond it, the universe continues, looking much the same as it does here. This picture becomes even more dramatic when combined with evidence about the geometry of the universe. Einstein's general theory of relativity tells us that the geometry of space, whether it is curved or flat, depends on the total energy density of the universe. If the energy density is above a critical value, space is positively curved, like the surface of a sphere. If it is below the critical value, space is negatively curved, like a saddle. And if it is exactly equal to the critical value, space is flat, like an infinite plane. Observations of the cosmic microwave background, particularly by the Planck satellite, have measured the geometry of the universe with extraordinary precision. The result is that the universe appears to be very close to flat, with any curvature being too small to detect. A flat universe is consistent with being infinite. If space is truly flat and extends without limit in every direction, then the observable universe is just a tiny bubble in an infinite sea of space, galaxies, and stars. The total universe would be infinitely large, containing infinitely many galaxies, infinitely many stars, and infinitely many planets. And in an infinite universe, the implications become profoundly strange. If the universe is truly infinite, and if the laws of physics are the same everywhere, then every possible configuration of matter must occur somewhere. Every possible arrangement of atoms, every possible planet, every possible civilization, every possible version of you must exist somewhere at some unimaginably vast distance. There would be a planet identical to Earth, with a person identical to you reading a script identical to this one, with only infinitesimal differences, repeated over and over and over across an infinite cosmos. This is not mysticism. It is a straightforward consequence of infinity and the finite number of ways that matter can be arranged in a given volume of space. The numbers involved are incomprehensibly large, with the nearest copy of you estimated to be about 10 to the power of 10 to the power of 29 meters away. A number so large that it makes the observable universe look like a grain of sand. But in an infinite universe, even that distance is nothing. Everything happens, somewhere. But this is just the first possibility. The second is more exotic and more speculative: the multiverse. The multiverse is not a single theory, but a collection of ideas from various branches of theoretical physics that converge on a common theme. Our universe may be just one of many. The most well-known version of the multiverse arises from the theory of cosmic inflation. Inflation is the theory that the universe underwent a period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang, expanding by a factor of at least 10 to the power of 26 in about 10 to the power of minus 33 seconds. Inflation was originally proposed to solve several puzzles in standard Big Bang cosmology, including why the universe is so homogeneous and isotropic on large scales, and why its geometry is so close to flat. Inflation has been extraordinarily successful, and its predictions match observations of the CMB with remarkable precision. But inflation has an unsettling consequence. In many versions of the theory, inflation does not end everywhere at the same time. Instead, it ends in localized regions, forming bubbles of normal space, while the space between the bubbles continues to inflate. Each bubble becomes a universe in its own right, with its own Big Bang, its own cosmic history, and potentially its own laws of physics. This is the eternal inflation scenario, and it predicts a multiverse, an infinite sea of eternally inflating space, studded with an infinite number of bubble universes, each one a separate cosmos with its own properties. Our observable universe would be one such bubble, a tiny island of normal space in an eternally inflating ocean. If the multiverse exists, the implications are staggering. Different bubble universes could have different physical constants, different numbers of spatial dimensions, different forces, and different particles. In some universes, gravity might be stronger, atoms might not form, or the universe might collapse into a black hole moments after forming. In others, conditions might be even more favorable for life than in our own. The vast majority of bubble universes might be completely inhospitable, sterile, and barren. Our universe, with its specific physical constants that allow for atoms, chemistry, stars, planets, and life, might be rare, special, and fortunate. This reasoning is called the anthropic principle. The physical constants of our universe are what they are because, in a multiverse of all possible constants, Only certain combinations allow for observers to exist, and we necessarily find ourselves in one of those observer-friendly bubbles. The anthropic principle is deeply controversial. Critics argue that it is not a scientific explanation at all, but merely a statement of observational bias. If we exist, of course we find ourselves in a universe that allows for existence. That does not explain why the physical constants have the values they do. Proponents counter that in a multiverse, there is no deeper why. The constants are not determined by some fundamental principle. They are determined by the random processes of bubble formation in an eternally inflating space, and we simply happen to be in a bubble where the dice fell favorably. Is the multiverse science? This is one of the most heated debates in modern physics. The hallmark of a scientific theory is that it makes testable predictions that can be confirmed or falsified by observation. The multiverse, by its very nature, seems to resist testing. We cannot observe other bubble universes. We cannot send probes to them. We cannot detect their light. How, then, can we test whether they exist? Some physicists argue that the multiverse can be tested indirectly. If eternal inflation predicts certain statistical properties of the CMB, and if those properties are observed, that would count as evidence for eternal inflation and, by extension, the multiverse. Others argue that this is not enough, that evidence for inflation is not the same as evidence for the multiverse, and that the existence of other universes is inherently unfalsifiable. The debate continues, and JWST, while it cannot directly observe other universes, contributes by constraining the models of inflation that give rise to the multiverse prediction. Every galaxy JWST discovers at extreme redshift, every measurement of the cosmic expansion rate, every characterization of the large-scale structure, refines our understanding of the physics of the early universe, including inflation, and thereby indirectly informs the multiverse debate. There is a third possibility for what lies beyond the edge, one that is perhaps the most philosophical. The universe might be cyclic. In this picture, the Big Bang was not the beginning of everything, but merely the latest in an endless series of cosmic cycles. Several specific theories embody this idea. Roger Penrose, the Nobel Prize-winning physicist, has proposed a model called conformal cyclic cosmology, or CCC. In CCC, the universe goes through infinite cycles called aeons. Each aeon begins with a Big Bang and ends when all matter has decayed, all black holes have evaporated, and the universe has reached a state of maximum entropy, a featureless sea of radiation. But Penrose argues that in such a state, the concept of scale becomes meaningless. If everything is radiation, and there are no particles with mass to define a standard of length or time, then the vast, cold, empty end state of one aeon is mathematically indistinguishable from the hot, dense, tiny initial state of the next aeon. The death of one universe is the birth of the next. Penrose has claimed to find evidence for this in the CMB, in the form of what he calls Hawking points, circular patterns in the temperature fluctuations that he interprets as the imprint of black hole evaporations in the previous aeon leaking through into our own. The claim is highly controversial, with most cosmologists not finding the statistical evidence convincing. But the idea is elegant and thought-provoking. Another cyclic model is the ekpyrotic universe, proposed by Paul Steinhardt and Neil Turok. This model draws on ideas from string theory, which suggests that our universe might exist on a three-dimensional membrane, or brane, embedded in a higher dimensional space. In the ekpyrotic model, our brane periodically collides with a neighboring parallel brane, and each collision triggers a Big Bang. The universe expands, cools, forms stars and galaxies, and then the branes approach each other again, heat up and collide, starting the cycle anew. In this picture, the Big Bang was not a singularity but a collision, and the universe extends infinitely far in time, both past and future, cycling endlessly through periods of expansion and collision. A third, cyclic possibility comes from loop quantum cosmology, a theory that applies the principles of quantum mechanics to the structure of spacetime itself. In loop quantum cosmology, the Big Bang is replaced by a big bounce. The previous universe was collapsing, getting denser and hotter, heading toward a singularity. But quantum gravitational effects, which become important at extremely high densities, prevented the singularity from forming. Instead, the collapse bounced, and the contraction turned into an expansion, creating our Big Bang. In this picture, our universe was born from the ashes of a previous universe, and our universe will eventually contract and bounce into a new one, and so on, forever. Each of these cyclic models offers a different answer to the question of what lies beyond the edge. In conformal cyclic cosmology, beyond the edge of our observable universe lies the continuation of our current aeon, and beyond that, the boundary between aeons, where the end of the previous universe meets the beginning of ours. In the ekpyrotic model, beyond the edge lies not just more of our universe but a higher dimensional bulk space containing other branes, other universes with their own histories and properties. In loop quantum cosmology, beyond the edge lies the remnant of a previous universe, a universe that collapsed and bounced into the one we inhabit. There is a fourth possibility that has gained attention in popular culture, though it remains firmly in the realm of philosophical speculation rather than empirical science: the simulation hypothesis. Proposed by philosopher Nick Bostrom in 2003, the simulation argument goes like this: if it is possible for a civilization to create detailed simulations of reality, complete with conscious beings who do not know they are simulated, then it is statistically likely that we ourselves are in such a simulation. The reasoning is simple. A single, sufficiently advanced civilization could create millions or billions of simulated universes. The number of simulated universes would vastly outnumber the one base reality. So, purely by the numbers, any given conscious being is far more likely to be in a simulation than in the base reality. In this picture, what lies beyond the edge of the observable universe might be the boundary of the simulation, the point where the computational resources of the simulator run out and the simulation simply stops. Or there might be nothing beyond the edge, because the simulation only renders the parts of the universe that its inhabitants can observe, like a video game that only generates the parts of the world that the player can see. This is a fascinating thought experiment, but it is not science in the conventional sense. There is no known way to test whether we are in a simulation, no prediction that the simulation hypothesis makes that can be confirmed or falsified by observation. Some physicists have speculated that there might be subtle glitches or patterns in the laws of physics or the cosmic structure that could hint at a simulated origin, but no such evidence has been found, and the idea remains on the far fringes of serious scientific discourse. So, where does all of this leave us? What is the answer to the question in the title of this video? What has James Webb discovered beyond the edge of the universe? The honest answer is that JWST has not discovered what is beyond the edge in the sense of directly observing whatever lies past the cosmic horizon. No telescope can do that. What JWST has done is something arguably more profound. It has pushed the boundary of the observable universe closer to the beginning of time than ever before, revealing the universe as it existed just 280 million years after the Big Bang. It has discovered galaxies that challenge our models, black holes that defy our expectations, and objects like dark stars and little red dots that we did not even know existed. It has mapped the invisible skeleton of dark matter that shapes the cosmos, detected the chemical fingerprints of possible biological activity on a distant world, and confirmed a tension in the expansion rate of the universe that may point to new physics beyond our current understanding. In doing all of this, JWST has expanded our knowledge of the cosmos more dramatically in just a few years than many previous telescopes did in decades. And every new discovery constrains what lies beyond the edge. Every galaxy at extreme redshift tells us that galaxy formation began extremely early, which tells us that the conditions for galaxy formation existed very early, which tells us something about the physics of the Big Bang and the period immediately after it, which tells us something about the larger universe beyond our horizon. Every measurement of the cosmic expansion rate tells us about the composition and evolution of the universe, which constrains models of what the universe looks like on scales far larger than the observable. Every observation is a puzzle piece, and while we may never see the complete picture, each piece narrows the possibilities and deepens our understanding. Let me now bring this journey together by talking about what comes next. JWST is not done, not by a long shot. With potentially 20 or more years of operational life ahead of it, the best discoveries may still be in the future. The telescope's observing programs are becoming more ambitious, more targeted, and more creative with each cycle. Future observations will push for even higher redshifts, probing deeper into the cosmic dawn, perhaps discovering galaxies or dark stars at redshift 15 or 16, corresponding to just 250 million years or even less after the Big Bang. If such objects are found, they will place even tighter constraints on the physics of the early universe and the nature of the first luminous objects. Future observations of K2-18b and other candidate biosignature planets will either confirm or rule out the presence of DMS and other biological markers, bringing us closer to answering the question of whether life exists beyond Earth. Future dark matter mapping campaigns will extend the 2026 map to wider areas and greater depths, providing an ever more detailed picture of the cosmic web and constraining dark matter models with increasing precision. And future measurements of Cepheid distances and the cosmic expansion rate will either resolve the Hubble tension or deepen it, with either outcome leading to transformative new physics. Beyond JWST, the next generation of telescopes is already being planned and built, and they will continue the revolution that Webb has started. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will complement JWST by surveying wide areas of the sky in infrared, providing a statistical view of galaxy populations that JWST's narrow field of view cannot match. Roman will be especially powerful for studying dark energy and dark matter through gravitational lensing and galaxy surveys. The Habitable Worlds Observatory, a next-generation space telescope concept, is being designed specifically to directly image Earth-like planets around nearby stars and search for biosignatures in their atmospheres. If funded and built, it would be the instrument that could definitively detect life on another world, building on the foundation that JWST has laid. On the ground, the extremely large telescope, with its 39-meter mirror, will provide spectroscopic capabilities that even JWST cannot match, allowing detailed chemical analysis of individual stars in distant galaxies and precise measurements of the expansion history of the universe. The LISA mission, a space-based gravitational wave detector, will detect the gravitational waves from merging supermassive black holes across cosmic time, providing a completely new window into the formation and growth of black holes in the early universe. And the Square Kilometer Array, a vast network of radio telescopes, will map the 21-centimeter emission from neutral hydrogen in the Dark Ages and the epoch of reionization, providing a view of the universe before the first stars that no optical or infrared telescope can offer. Together, these instruments will build a comprehensive picture of the universe from the Big Bang to the present day, filling in the gaps in our knowledge and pushing the boundaries of discovery even further. We are living at the beginning of a golden age of astronomy, a time when the questions that have haunted humanity for millennia, questions about the origin, structure, and fate of the universe, about the existence of life beyond Earth, about the nature of dark matter and dark energy, are finally within reach of scientific investigation. We will not answer all of them in our lifetimes, but we will answer some, and the answers will change everything. Let me leave you with this thought. The James Webb Space Telescope is, in a sense, the universe's way of understanding itself. We are made of atoms that were forged in the furnaces of ancient stars, atoms that have been part of gas clouds and planets and possibly other living things before they became part of us. The matter in your body has been around since the Big Bang, recycled and reconstituted over 13.8 billion years of cosmic evolution. When you look at a JWST image of a galaxy at the edge of the observable universe, you are not just looking at something far away. You are looking at your own origin. The stars in that galaxy, the ones that burned and died billions of years ago, produced some of the elements that eventually became the matter in your body. You are connected to those ancient lights by an unbroken chain of atomic heritage stretching back to the dawn of time. And the fact that you can sit here right now and understand that connection, the fact that the universe has produced beings who can look back at their own origin and comprehend it, that is perhaps the most extraordinary thing of all. The universe did not have to be comprehensible. It did not have to produce beings capable of understanding it. The laws of physics did not have to be elegant. The cosmos did not have to be beautiful. But it is comprehensible, it is elegant, it is beautiful, and we are here to witness it. James Webb is our eye on the infinite, and what it sees, looking outward toward the edge and backward toward the beginning, is a universe that is stranger, richer, more violent, more creative, and more deeply mysterious than any of us imagined. Galaxies that should not exist, black holes that formed in an instant from the collapse of pristine gas, stars that may be powered by the dark matter that makes up most of the universe's mass, a cosmic web of invisible matter that determines where every galaxy is allowed to form, chemical whispers on a distant world that might, just might, be the breath of alien life. A universe that is expanding at a rate that our own physics cannot fully explain. And beyond it all, past the last photon, past the cosmic horizon, a vastness that may be infinite, that may contain other universes with other laws of physics, that may cycle eternally through death and rebirth, or that may hold something so far beyond our current imagination that we do not even have words for it yet. That is what James Webb has discovered beyond the edge of the universe. Not a final answer, not a neat conclusion, but a breathtaking expansion of the territory of the known, and an even more breathtaking revelation of the immensity of the unknown. We are not at the end of the story. We are not even at the middle. We are at the very beginning. The golden mirror is still looking. The photons are still arriving. The data is still being analyzed, and the universe is still revealing its secrets, one ancient photon at a time. If this video expanded your understanding of the cosmos even a fraction of how much the universe has expanded since the Big Bang, then do me a favor. Hit that like button. Subscribe to this channel, turn on notifications, and drop a comment below telling me which discovery from this video blew your mind the most. Was it the impossible galaxies, the dark matter stars, the biosignatures on K2-18b, the Hubble tension, the little red dots, Or the idea that beyond the edge there might be infinite copies of you. I want to hear your thoughts. I read every comment. Share this video with someone who loves space, someone who lies awake at night staring at the ceiling and wondering what is out there. Let us grow this community of curious minds, because the universe is too big, too strange, and too beautiful to explore alone. And until next time, keep looking up. The answers are out there, somewhere beyond the edge. And we are getting closer every single day. End.